laws of logarithms are super important for this topic. The laws of logarithms will allow us to give us the tools to solve logarithmic equations, using these for a wide variety of different problems, and they simply are very powerful. So the first log law is the equivalent law that we know for indices, which says a to the power of n times a to the n. As we know, you add the powers. I would like to derive and to prove the corresponding result for this in terms of logarithms. So the first thing we're going to do is we're going to say that log base a of x is equal to n. Okay? So log base a of m is equal to x. In other words, a to the power of m is equal to x. Using the definition of the log law, using the definition of the log which we did in the previous video. This means a to the m is x. I would also like to say log ay is n, which similarly means a to the power of n is equal to y. Now we know from the currently existing laws of indices, this one in particular, that a to the m times a to the n is this. So a to the m we've now said is x, so that becomes x. A to the n we said is y. And I don't specifically have a replacement for a to the n plus n, so I'm just going to leave it as it is. Now, x times y we can just write as xy. And now let's use the definition of the log, because the definition of the log can be used where you've got a base, a power, and a result. The fact that the result is xy, the fact that the power is m plus n doesn't matter. We said that log of the base for the result xy equals m plus n. I've rewritten this as this. Remember when we stated the definition of the logarithm, we said log a of b equals x is the same as a to the power of x is equal to b. And that's what we've got here. Now m and n, if we go back here, have their own equivalent. Look, m was equal to this, and n was equal to that. So in other words, log a xy is m, which is this, plus n, which is this, and that is the first log law. When you are logging for a specific base a product, okay, x times y, two things multiplied together, you can split them out using addition. Log a x plus log a y. It's the equivalent of this. We know that you multiply two terms with the same base and different powers, you add the powers. That's what this is doing here. When you log a product, you add the specific x and y. So we have the first log law, log a xy equals log a x plus log a y. I want to draw your attention to a couple of important things to note where you could potentially read that and think, oh, it's easy, yeah, it makes sense. Just be careful that in order to add two logarithms, the coefficients have to be 1. Okay? So for example, if I've got log base 5, 10, and log base 5, 2, because the coefficients are both 1, I can combine them. I can use the logarithm law this way here. And you can multiply the x and the y, which in this case is 20. So I can combine those two logarithms together and write log 520. The same is the other way. if I've got log a xy as a base, I need to make sure that the coefficient there is 1. Otherwise, we cannot just add the logs. We can't ignore the fact if there are coefficients there. You may ask, what do I do if there are coefficients? Well, we'll see when we learn the third log law. Now, the law where we know for indices that when you have a to the power of x divided by a to the power of y, where we subtract the powers, works in a very similar way. So you can prove it in a very similar way, and you can actually repeat a similar proof that I did for this one, and to arrive at this result here. That's the second log law. The second log law states that if you have to log a quotient, two things being divided together, you can subtract the separate logs. Most of the time, I must add, that you'll be using these laws from the right to the left. That if you have two logs subtracted, you can combine the two logs together and perform a log of a quotient. However, once again, the coefficients have to be 1 for you to do that. I'd like to prove the final log law. This is log number 1, 2, right. The final log law. So what I'm going to do is as follows. I'm going to say that log AX is capital M. Which means, using the definition, a to the power of m is x. Let's write that down. Now, from here, what I'd like to do is raise both sides to the power of n, something else. So let's do a to the power of m, to the power of n, which means that x gets raised to the power of n. We know from our work on indices that a to the power of m in brackets and then n on the outside would be multiplied. And we're almost coming full circle. What I'm now going to do is translate that back in terms of the logarithm, because remember, you always have the option to turn a statement into logarithmic form if you have a base, a certain power, and a result. Just think about this as a result. Don't think of it as x to the power of something. X to the power of n would be a number. So we could write this as log base a of the result is equal to log a of x n mn. Okay, just using the definition of the log. And then that m over there we defined as log ax. So let's put that in there. And then we get the following result. Log a x to the power of n is equal to log ax multiplied by n. I'm going to put the n first. N multiplied by log ax. This result will be very, very helpful. Do you remember that I said that if you have coefficients in front of these terms, you cannot use that law? So what do? Do we just not add log terms that have coefficients? Of course not. This law will take care of any coefficients that you do not want. Because look, if you have a coefficient in front of a log, what does this say? The log law says any coefficient in front of a log can be passed up and become the power of whatever is inside the log. N log ax becomes log ax to the power of n. What's happened to that n? It's become this power. That's the only thing that's happened. This result is the equivalent of the very popular indices, the very popular law of indices, which says x to the power of a, all in brackets, to the power of b is x to the power of a, b. So here are our three log laws. 1, 2, and 3. So just to show you what kind of activities we could, so just to show you what kind of operations we can use with these logarithms, take a look at this. Let's suppose I have log 5 10 minus log 5 of 5. Well, when you look at this, you say to yourself, okay, I'm subtracting two logs. Which law uses subtraction of logs? It's not that one. Ah, it's that one. Right? This tells me I can subtract two logs as long as the coefficients are 1, and then I can divide them. Are the coefficients of 1? Yes. So I can write that as one single log of log 5, 10 divided by 5. And if you can do 10 divided by 5 and simplify it further, you should. So that becomes log 5, 2. Now, let's look at this expression. Right, we're going to add these two terms together, these logs. Now, really, where this is going is that where you have multiple log terms, you want to combine them as far as you can to one single log. So when you're looking at this, you shouldn't be saying, okay, well, what's wrong with that? Let's just leave it like that. No, you can combine logs. It's just a question of how. So this one here, you have to be careful. Why do you have to be careful? Because there are coefficients. We are adding logs. There's a 2 there and a 4 there. I cannot simply multiply the 8 and the 7 from this law here because there are coefficients there and there. To use that law, and I want to use that law, I need to ensure that there are no coefficients. And what did we say? The law that takes care of coefficients for us is this one over here. If you have a coefficient, k, in front of a log, and you want to get rid of it, use this law from right to left. It pops that k as a power. That's exactly what we are going to do. So I don't want that 2 there, so use the law number 3 to pop that up at the top here. So that becomes log 364. I also don't want that coefficient there, so I've got to pop that as a power of 7, which is 2,401. And now we can add the two logs. There are no coefficients, so you can use this law, and you can multiply the 64 and the 2,401. 5, 3, 6, 6, 4. As a quick exercise, I'd like you to combine the two logs in each of the following two questions, arriving at an answer of a single logarithm for both of these. Okay, so your answer can only have one log, not two. So have a go at this and stop the video, press play, and we'll go through it. So let's see. So we're adding two logarithms in the first question, but we cannot have coefficients. So, like we just saw, the third log law pushes these coefficients up there. So that becomes log 5, 3 squared, which is 9. The 3 needs to be taken care of. That will go up there using the third log law again, and that becomes log 5, 2 cubed, which is 8. Once you've got two logs with a coefficient of 1, you can use log law number 1 and multiply the 9 and the 8. So the answer is log 5, 72. And a lot of the time we will leave these questions as logarithms. The fact log 572 you can do on the calculator, that's very nice, but that's actually the exact value. That's an exact value. If you use on the calculator, you'll have to round it to a decimal. Right, the second one, we are subtracting logs, so I want to use this law, except, although the coefficient there is 1, the coefficient there is not 1. So what we will do is the log 10 3 I will leave alone. For log 10 half, I will push the power 4 up there. A half to the power 4 is 1 over 16. And now we can subtract logs using the second law and divide. So we get log 10 3 divided by 1 over 16. You should not leave it there. This has nothing to do with logs. This is just simplification. 3 divided by 1 over 16. The 16 comes to the top. Just using division of fractions. And you get log 10 48. That's nicer than that.